scientists confront the question, what lies beyond the universe? Late one night in March 2024, cosmologist Dr. Elena Vasquez was reviewing data from the James Webb Space Telescope when she noticed something that made her coffee go cold. At the very edge of the observable universe, in a region so distant that light had been travelling toward us for 13.4 billion years, she detected a pattern. Not the random distribution of galaxies you'd expect, but structure, a systematic alignment suggesting something was pulling on these ancient galaxies from beyond what we can see. Her hands trembled as she ran the analysis again and again. The pattern remained. Something existed out there, past the cosmic horizon, influencing what we could observe. For the first time in human history, we might have indirect evidence of what lies beyond the universe itself. But the implications of that evidence would force scientists to confront a question they'd always considered meaningless. If the universe is everything, what could beyond even mean? What you're about to discover will fundamentally challenge your understanding of existence itself. Before we can explore what might lie beyond the universe, we need to understand what we mean by universe and why the question of what lies beyond it seems paradoxical. The universe, as astronomers define it, is everything that exists, all matter, energy, space, and time. It encompasses every galaxy, star, planet, atom, and photon. By definition, there cannot be anything outside the universe because the universe includes everything. Yet this definition creates a puzzle. When we look into space, we can only see so far. Light travels at a finite speed, and the universe has a finite age, approximately 13.8 billion years. This means we can only observe objects whose light has had time to reach us since the Big Bang. The distance to this cosmic horizon, the edge of the observable universe, is not 13.8 billion light-years. Due to cosmic expansion, space itself has been stretching while light travelled toward us, so the most distant objects we can see are now about 46.5 billion light-years away in all directions. This creates a sphere, centred on Earth, about 93 billion light-years in diameter. This is the observable universe, the region of space from which light has had time to reach us. But here's the crucial question. Does the universe end at this horizon? Almost certainly not. The observable universe is simply the portion we can see. It's like standing in a vast forest where fog limits your vision to 100 feet in every direction. The visible area is a circle 200 feet across, but the forest extends far beyond what you can see. The fog doesn't mark the forest's edge, just your visibility limit. Similarly, the cosmic horizon doesn't mark the universe's edge, it marks the limit of our observation. Beyond that horizon, space almost certainly continues, containing more galaxies, stars, and planets we'll never see, because their light hasn't had time to reach us yet, and due to accelerating cosmic expansion, never will. So when we ask, what lies beyond the universe, we're really asking several different questions. What lies beyond the observable universe? More universe, presumably much like what we can see. Does the universe have an edge? And if so, what's beyond that edge? Could there be other universes, separate regions of existence disconnected from ours? What is the universe embedded in? Does it exist within something larger? These questions push physics, cosmology, and philosophy to their limits. Let's explore them one by one. The first question, what lies beyond the observable universe, depends critically on the universe's geometry and whether it's finite or infinite. Einstein's general relativity shows that space itself can curve, not metaphorically, literally. The geometry of space is determined by its matter and energy content. There are three basic possibilities. Imagine an ant crawling on a basketball. The surface is finite, it has a specific area, but it has no edge. The ant could walk forever without falling off or reaching a boundary. If the ant walked far enough in any direction, it would eventually return to its starting point. A positively curved universe would be similar, but in 3 dimensions. Space would curve back on itself. The universe would be finite, containing a specific, limited volume, but boundless, with no edge or boundary. Travel far enough in any direction, and you'd eventually return to where you started. In such a universe, what lies beyond the observable universe is more universe, curving around. Eventually that beyond curves back to connect with the observable region, like the backside of the basketball connects to the front. Imagine the ant on a saddle or a Pringle chip, a surface that curves away from itself in a hyperbolic shape. Such a surface extends infinitely in all directions. A negatively curved universe would be infinite in spatial extent. It would contain infinitely many galaxies, infinitely many stars, infinitely many atoms. What lies beyond the observable universe would be more universe, extending forever. In this scenario, beyond means infinite cosmos, continuing without end. There is no edge, because infinity has no edge. The third possibility is that space is flat, Euclidean geometry holds, parallel lines never meet, and the angles of triangles sum to 180 degrees. A flat universe could be either finite or infinite. Finite flat universe. Like the surface of a Pac-Man game, when you go off one edge, you appear on the opposite edge. The topology is different from ordinary flat space, creating a finite volume that wraps around on itself. Infinite flat universe. Space extends forever in all directions, like an infinite sheet of paper. This appears to be the simplest case and matches our observations. What do observations tell us? Scientists measure the universe's curvature by looking at patterns in the cosmic microwave background, the afterglow of the Big Bang. Temperature fluctuations in this ancient light carry information about space's geometry. Multiple satellites, including WMAP and Planck, have measured the CMB with extraordinary precision. The verdict: space appears to be flat to within about 0.4% margin of error. This means the universe is either exactly flat or so close to flat that we can't detect the difference. Given this flatness, most cosmologists believe the universe is infinite, extending forever beyond our observable horizon. If true, this has profound implications. Infinite space contains infinite matter. If the universe extends forever and matter is distributed roughly uniformly, as observations suggest, then there are infinitely many galaxies, infinitely many stars, infinitely many planets. Everything that can happen does happen infinitely many times. You have infinite duplicates. In an infinite universe with random variations, every possible arrangement of matter appears somewhere. That includes copies of you, identical down to the atoms, living identical lives elsewhere. Far beyond the observable universe, there are infinitely many yous reading this exact sentence at this exact moment. This seems bizarre, but it's a straightforward consequence of infinity plus randomness. If space is infinite and matter is distributed randomly, then any finite configuration, like your brain with its precise pattern of neurons, appears infinitely many times. The question changes meaning. If the universe is infinite, asking, what's beyond the universe, is like asking, what's north of the North Pole? The question contains a false assumption. There is no beyond, because infinity has no boundary. But this doesn't end the inquiry. Even if our spatial universe is infinite, other questions remain. The most scientifically respectable answer to what lies beyond the universe is other universes. This isn't science fiction. Multiple independent lines of reasoning in modern physics suggest we might live in a multiverse. Level 1 multiverse, infinite space. As just discussed, if space is infinite, then beyond the observable universe lies more space with more galaxies. Max Tegmark, a cosmologist at MIT, calls this a level 1 multiverse, other regions of the same space beyond our cosmic horizon. These aren't separate universes in different dimensions or realities, they're just distant parts of the same universe, so far away that light from them will never reach us. But there's a wrinkle. Due to quantum mechanics and cosmic inflation, different regions of infinite space might have different physical properties. During inflation, the exponential expansion in the universe's first split second, quantum fluctuations were stretched to cosmic scales. These fluctuations created slight differences in density that eventually became galaxies and the cosmic web's structure. But quantum mechanics is probabilistic. Different regions might have experienced different quantum outcomes during inflation, leading to different values for physical constants or even different laws of physics in different cosmic regions. If so, our observable universe isn't just one region among many identical regions, it's one region among many different regions, each potentially with different physics. We happen to exist in a region with physics compatible with life because, obviously, we couldn't exist in regions with incompatible physics. Level 2 multiverse, eternal inflation. Cosmic inflation, that exponential expansion in the universe's first instant, might not have happened just once. Many models of inflation are eternal. Inflation stops in some regions, creating bubble universes like ours, but continues in other regions, which then spawn more bubbles and so on forever. Each bubble would be a separate universe with its own Big Bang, its own expansion history, and potentially its own physical laws, depending on how fields settled during that bubble's formation. These bubble universes would be separated by eternally inflating space. You couldn't travel from one bubble to another because the space between them expands faster than light, growing without limit. Our universe would be one bubble in an infinite froth of bubble universes, each causally disconnected from the others. Beyond, our universe would be other universes, forever unreachable. Alan Guth, who pioneered inflation theory, believes eternal inflation is likely. The basic picture that our universe is a small part of a vastly larger multiverse is by now a standard part of cosmology, taught in graduate courses and mentioned frequently at major conferences. Level 3, multiverse, many worlds quantum mechanics. Quantum mechanics has an interpretation crisis. When you measure a quantum system, say checking an electron's spin, you get a definite result, spin up or spin down. But before measurement, the electron existed in a superposition of both states simultaneously. What happens during measurement? The Copenhagen interpretation says the wave function collapses to a single outcome. But this collapse is mysterious. Nothing in quantum mechanics equations describes it. The many worlds interpretation, proposed by Hugh Everett in 1957, eliminates collapse. Instead, all possible measurement outcomes occur, but in different branches of reality. When you measure the electron's spin, the universe splits. In one branch you observe spin up, in another branch you observe spin down. Both outcomes are real, occurring in parallel universes. Every quantum event, and quantum events happen constantly, trillions upon trillions per second, splits the universe into multiple branches. The number of parallel universes grows exponentially. In this view, beyond, our universe are innumerable parallel universes, exploring every quantum possibility. A version of you exists in universes where you made different choices, where quantum events in your brain produce different thoughts. Many physicists take many worlds seriously. It's mathematically elegant. It just takes quantum mechanics equations literally, without adding extra assumptions about wave function collapse. But it's philosophically expensive. It posits an infinity of unobservable universes. Level 4 multiverse, mathematical democracy. The most radical multiverse proposal comes from Max Tegmark. He proposes that every mathematically consistent structure exists physically as a universe. The reasoning: our universe appears to be described by mathematics. Physics is mathematical. If you strip away all the matter and energy, you're left with mathematical structure, relationships, symmetries, patterns. Tegmark asks, why does this particular mathematical structure exist physically while others don't? Maybe they all do. Every possible mathematical structure that's self-consistent exists as a universe somewhere in the level 4 multiverse. This includes universes with different numbers of dimensions, different particles, different forces, different or no quantum mechanics, different or no relativity. Every possible physics that can be consistently described mathematically. Most of these universes would be incompatible with life. Most would be incomprehensibly alien, but they'd all exist, with equal reality. In this framework, our universe isn't special. It's one mathematical structure among the infinite ensemble of all possible structures. Beyond, our universe is every other possibility, all equally real, all instantiated somewhere in the level 4 multiverse. This is speculative, controversial, and possibly untestable, but it represents the ultimate answer to what's beyond, everything else that could possibly be. The problem of nothing. What's the universe in? Children often ask, what is space expanding into? It seems like a natural question. If the universe is expanding, mustn't it be expanding into something? The standard answer is that this question is based on a misconception. Space isn't expanding into anything. Space itself is what's expanding. There's no outside space for it to expand into. But this answer feels unsatisfying. It's mathematically correct but philosophically frustrating. Surely the universe must be embedded in something. The bulk, higher dimensions. Some physics theories propose that our universe is embedded in a higher dimensional space called the bulk. String theory, for instance, suggests reality has more dimensions than the 3 spatial dimensions plus time we experience. Various versions propose 10, 11, or even 26 total dimensions. If extra dimensions exist, our universe might be a 3-dimensional brane, short for membrane, floating in higher dimensional space. Everything we observe, all particles, forces and fields, would be confined to our brain. We couldn't perceive the extra dimensions because we can't move through them, but gravity might propagate through the bulk. This could explain why gravity is so much weaker than other forces. Its strength gets diluted across extra dimensions. In this picture, beyond our universe would be higher dimensional space, potentially containing other branes, other universes. These parallel universes could be micrometers away in the extra dimension, but forever unreachable because we can't move off our brain. When branes collide in the bulk, the theory goes, it releases enormous energy, potentially creating a Big Bang. Our universe might have formed from such a collision. Other collisions might create other universes. This is respectable physics, published in peer-reviewed journals by serious physicists like Lisa Randall and Raman Sundram. But it remains speculative. We have no direct evidence for extra dimensions or branes. Mathematical space, the Platonic realm. Some philosophers and physicists argue that the universe doesn't need to be embedded in physical space. It could be embedded in mathematical or logical space. Mathematical objects don't exist in physical space. The number 7 isn't located anywhere. It's an abstract entity. Yet mathematical structures have relationships, organization and existence of a sort. If the universe is fundamentally mathematical, as Tegmark proposes, then perhaps it exists in the space of mathematical possibilities, the way a particular equation exists within the space of all possible equations. Beyond the universe, then, would be the realm of pure mathematics, Plato's realm of forms, where all possible structures exist in timeless, spaceless perfection. This sounds mystical, but it's how many mathematicians think about their discipline. The Mandelbrot set exists in some sense, even though it's not made of atoms or energy. Its structure is objective, discoverable, and the same for all observers. If the universe is similar, a particular mathematical structure instantiated somehow, then it exists in mathematical space, and beyond it are other mathematical structures, other laws, other symmetries, other possible worlds. God's mind, the theological answer. Religious traditions offer another answer. The universe exists within the mind of God or some ultimate reality that transcends physical existence. This isn't just ancient theology. Some modern philosophers of physics take this seriously. Philosopher George Berkeley argued that material reality is perception in the mind of God. Physicist John Wheeler proposed that reality emerges from observer participation, that the universe is a self-excited circuit where conscious observers help bring reality into existence. These views are controversial and largely abandoned in mainstream physics, but they represent historical attempts to answer what the universe is embedded in: consciousness, mind, or some form of existence more fundamental than physical reality. The holographic principle, reality as projection. One of the strangest ideas in modern physics suggests that the universe might be a hologram, a 3-dimensional projection of information encoded on a 2-dimensional surface. This emerges from black hole physics. When matter falls into a black hole, information about it seems to disappear behind the event horizon. But quantum mechanics says information can't be destroyed. This creates the black hole information paradox. Physicist Leonard Susskind and others proposed a solution. Information isn't lost inside the black hole. Instead, it's encoded on the event horizon's surface. The 3-dimensional interior is actually a holographic projection of information on the 2-dimensional boundary. Then Gerard 't Hooft and Juan Maldacena showed this isn't just about black holes. It might apply to the universe itself. The entire 3-dimensional universe might be a holographic projection of information encoded on a distant 2-dimensional boundary. If true, this radically changes what beyond means. The 3-dimensional space we inhabit would be an illusion, a projection from a lower dimensional surface. Beyond our perceived 3D universe would be the 2D surface where information is really stored. Think of a hologram on a credit card. It looks three-dimensional, but all the information is encoded in two-dimensional interference patterns on the card's surface. Similarly, our apparently 3D universe might be projection from a 2D screen at the cosmos's boundary. What exists at this boundary? What is the screen made of? Nobody knows. The holographic principle is mathematically rigorous and emerges from string theory, but its physical interpretation remains mysterious. The edge of time, before the Big Bang. So far we've focused on spatial, beyond, what's outside the universe's edges or past its horizon. But there's another beyond, temporal beyond. What came before the Big Bang? For decades the standard answer was nothing. Time itself began at the Big Bang. Asking what came before is like asking what's north of the North Pole. The question doesn't make sense because you can't go further north than the northernmost point. But recent theories challenge this. Eternal inflation's prehistory. If our universe is a bubble in eternal inflation, then before our Big Bang was the inflating space from which our bubble emerged. Time existed before our local timeline began, but it was time in the larger inflating space, not in our universe yet. Cyclic cosmology. Physicist Roger Penrose proposes conformal cyclic cosmology. The universe goes through infinite cycles. Each cycle begins with a Big Bang and ends in the far future when only massless particles remain. Through mathematical transformation, this end state becomes identical to a Big Bang, starting the next cycle. In this view, before our Big Bang was the previous cycle, a previous universe that ran its course and transformed into ours. Similarly, Paul Steinhardt and Neil Turok's ekpyrotic model proposes cycles where our universe is one of two branes in higher dimensional space. These branes periodically collide, with each collision appearing as a Big Bang from inside our brane. Before our Big Bang was the previous collision. Quantum creation. Some theories propose the universe emerged from a quantum fluctuation in a pre-existing quantum field or quantum foam. Stephen Hawking's no-boundary proposal suggests the universe has no beginning in time. It emerges naturally from a timeless quantum state. This is mind-bending. There's no before the Big Bang. Not because time started then, but because time is an emergent property that doesn't exist in the quantum state from which the universe emerged. The simulation hypothesis. A more radical idea. Our universe might be a simulation running on a computer in some higher reality. Before our Big Bang would be when the simulation started. Beyond our universe would be the reality where the computer exists. Philosopher Nick Bostrom argued that if civilizations can survive to technological maturity, such civilizations develop simulation technology. They choose to run simulations of their evolutionary past. Then, simulated beings vastly outnumber real beings, and statistically, you're probably simulated. If our universe is a simulation, beyond is the base reality where the simulators exist. A reality that might have completely different physics, dimensions, or principles than ours. The anthropic principle. Why this universe? Even if we accept that other universes exist, through inflation, many worlds, or mathematical instantiation, a question remains. Why do we find ourselves in this particular universe? The anthropic principle provides an answer. We observe this universe because its properties allow observers to exist. We couldn't find ourselves in universes incompatible with life. This comes in weak and strong versions. Weak anthropic principle. We observe the universe to have properties compatible with our existence because, if it didn't, we wouldn't be here to observe it. This is tautological, but true. Strong anthropic principle. The universe must have properties that allow life to develop at some point. This suggests the universe was somehow designed or selected for life, a controversial claim. The anthropic principle becomes powerful when combined with multiverse theory. If countless universes exist with randomly varying properties, most will be sterile, incompatible with any life. Only tiny fractions will have the right force strengths, slightly different and atoms wouldn't form, the right expansion rate, faster and galaxies never form, slower and the universe collapses. The right particle masses, different and chemistry would be impossible. We necessarily find ourselves in one of the rare habitable universes, even though most universes are lifeless. This explains why our universe seems fine-tuned for life, without requiring a designer. It's selection bias. We can only observe universes where observation is possible. But critics argue this doesn't really explain anything. It just says, we exist in a universe compatible with existence, without explaining why any universe exists at all. Behind all questions about what's beyond the universe lurks a deeper mystery. Why does anything exist at all? Philosopher Gottfried Leibniz called this the fundamental question of metaphysics. Every explanation for the universe's existence seems to require something else. The universe came from the Big Bang. What caused the Big Bang? Quantum fluctuation. What is the quantum field and why does it exist? Eternal inflation. What is the inflating field and why does it exist? Mathematical multiverse. Why do mathematical structures exist at all? God. What is God and why does God exist? Every answer pushes the question back one level. Some philosophers argue this regress must terminate somewhere. There must be a necessarily existing thing that requires no further explanation. This could be God in theology, the quantum vacuum in physics, mathematical structure in Tegmark's framework, consciousness in idealist philosophy, blind contingency in existentialism. Things just exist without reason. Others argue the question itself is flawed. Physicist Lawrence Krauss argues nothing is unstable. Quantum mechanics predicts that something must arise from nothing. But critics point out his nothing is actually quantum fields obeying physical laws, not true nothing. Perhaps, why is there something rather than nothing, is unanswerable, not because we lack information, but because the question assumes there could be a state of nothing, which might be incoherent. If mathematical structures exist necessarily, you can't make 2 + 2 = 5, and if the universe is a mathematical structure, then perhaps it exists necessarily. There couldn't be nothing, because nothing isn't a coherent possibility. What we can never know. Some questions about what lies beyond the universe might be permanently unanswerable. The cosmological horizon. Due to cosmic expansion, we'll never see beyond a certain distance. Light from regions beyond our horizon will never reach us, not because it's travelling too slowly, but because space expands faster than light. This creates a fundamental observational limit. We can theorize about what's beyond, but we can never test those theories through observation. Other universes. If other universes exist, through eternal inflation, many worlds, or other mechanisms, and if they're causally disconnected from ours, we might never detect them. Some argue this makes multiverses non-scientific, because they're untestable. Others argue they're legitimate science if they're predictions of well-tested theories, like inflation or quantum mechanics. The limits of mathematics. Gödel's incompleteness theorems prove that any sufficiently complex mathematical system contains statements that can't be proven true or false within that system. You need a larger system to prove them, but then that larger system has its own unprovable statements. If reality is ultimately mathematical, there might be truths about existence that are forever unprovable, even in principle. Some questions might not just be unanswered, but unanswerable. The observer problem. Quantum mechanics suggests observers play a role in defining reality through measurement, but this creates a paradox. To study the universe as a whole, you'd need to be outside it, observing it. But there is no outside. This might fundamentally limit what we can know about the universe's global properties or what lies beyond it. The cutting edge. What current research suggests. Despite these limitations, cosmologists continue pushing toward answers. The CMB anomalies. The cosmic microwave background isn't perfectly uniform. There are tiny temperature fluctuations, the seeds of galaxies, that match predictions precisely. But there are also anomalies, large-scale patterns that shouldn't exist if the early universe was random. One is the axis of evil, a suspicious alignment of temperature fluctuations along a preferred direction. Some researchers argue these anomalies might be evidence of collisions with other bubble universes in the multiverse, effects from physics beyond the observable universe, imprints from before the Big Bang. These interpretations are controversial, but the anomalies are real and unexplained. Gravitational wave cosmology. Gravitational waves, ripples in spacetime from violent cosmic events, are opening new ways to study the universe. Future detectors might detect gravitational waves from the Big Bang itself, find evidence of cosmic strings, one-dimensional defects in spacetime from the early universe, observe signatures of colliding branes in extra dimensions. These observations could provide evidence for theories about what lies beyond. Quantum gravity theories. String theory, loop quantum gravity, and other quantum gravity approaches might resolve what happens at the Big Bang singularity or inside black holes. If successful, they could reveal whether time existed before the Big Bang, space extends beyond what we observe, other dimensions exist. These theories remain incomplete, but progress continues. The Swampland program. String theorists are mapping the landscape of possible universes predicted by string theory and identifying the swampland, configurations that seem mathematically possible but are actually inconsistent with quantum gravity. This might eventually constrain multiverse theories, ruling out certain types of other universes as impossible, even though they seem mathematically consistent at first. The philosophical implications. The question, what lies beyond the universe, isn't just scientific, it's deeply philosophical. The answer affects how we understand existence, meaning, and our place in reality. If the universe is all there is, if there's no beyond, if the universe is finite and contains all of existence, then we're cosmically unique. This universe, these laws, this history, it's all there is. Nothing else could have been. Existence is brute fact. The universe just exists, without further explanation. Why? Has no answer. We're profoundly alone, not just in the sense of no aliens, though possibly that too, but in the sense that reality consists of only what we observe. This is philosophically stark but simple. Occam's razor might favour it. If countless universes exist, if there's a multiverse, especially a level 4 mathematical multiverse, then we're insignificant. Our universe is one among infinite others. Nothing special about us or our laws. Everything that can happen, does happen. All possibilities are realised somewhere. Every choice you could make, you do make in some universe. Fine-tuning is explained. The universe seems designed for life, only because we couldn't observe a universe not compatible with observers. Meaning becomes relative. If all possibilities exist, nothing is unique or special in an absolute sense. Meaning must be constructed locally, not found cosmically. This is philosophically dizzying, but potentially resolves many puzzles about why our universe has the properties it does. If the universe is embedded in something greater, if the universe exists within higher dimensions, the bulk or some substrate like mathematics or consciousness, there are deeper levels of reality. What we experience isn't ultimate, it's an emergence or projection from something more fundamental. Understanding is hierarchical. To truly understand our universe, we'd need to understand what it's embedded in, potentially an infinite regress. Exploration might be possible. If other universes are in the same bulk or mathematical space, perhaps future civilizations could access them. This is philosophically rich, but speculative. Perhaps the most honest answer to what lies beyond the universe is we don't know and we might never know. But this uncertainty isn't a failure, it's a frontier. Every answer we've found has revealed deeper questions. Every horizon we've reached has shown further horizons beyond. The observable universe is 93 billion light-years across, containing perhaps 2 trillion galaxies, each with hundreds of billions of stars. The scale is already incomprehensible. If our universe is infinite, or if it's one among countless others, the scale expands to literal infinity. If it's embedded in higher dimensions, or is a mathematical structure among all possible structures, the conceptual depth becomes infinite as well. We're creatures evolved to hunt gazelles on the African savanna. The fact that we can even ask what lies beyond the universe and make progress toward answers, the fact that mathematics and observation can reveal truths about reality on cosmic scales, is extraordinary. Maybe we'll never know what lies beyond. Maybe the question is somehow malformed. Maybe there is no beyond, the universe is all. Or maybe future discoveries will reveal answers we can't currently imagine. Maybe gravitational waves will carry information from beyond the horizon. Maybe we'll find evidence of parallel universes. Maybe we'll discover we're in a simulation and find ways to communicate with the simulators. Maybe we'll develop mathematical frameworks that make beyond the universe a meaningful, addressable question. The uncertainty should inspire not frustration, but wonder. The universe is under no obligation to be comprehensible to evolved primates on one planet. The fact that it's comprehensible at all is miraculous. The fact that we can push understanding to the very edges of existence and beyond is humanity's greatest achievement. So what lies beyond the universe? More universe? Other universes? Higher dimensions? Mathematical space? God's mind? A computer simulation? Nothing at all? The answer is, we're working on it, and the quest to find out will likely reveal truths about reality stranger and more wonderful than any answer we can currently imagine. The universe has surprised us before, with quantum mechanics, relativity, the expanding cosmos, dark energy, and more. It will surprise us again. The question isn't whether our current understanding is complete. It never is. The question is whether we're brave enough to keep looking beyond every horizon we reach, knowing each answer reveals new mysteries, knowing we might never reach ultimate answers, but knowing the search itself expands what it means to be human. Beyond the universe lies the unknown, and the unknown has always been humanity's greatest teacher, greatest challenge, and greatest gift. The search continues, the mystery remains, and that's exactly how it should be. If this journey to the very edge of existence and beyond left you with more questions than answers, that's the point, because the universe's deepest mysteries are designed to expand our minds, not comfort them. Hit that subscribe button right now if you want to keep exploring the questions that exist at the boundary between science, philosophy, and the nature of reality itself. Drop a comment below. Do you think the universe is all there is? Or are we one bubble in an infinite multiverse? Which answer would you want to be true? And why? Smash that like button if you enjoyed having your understanding of existence fundamentally challenged. Because the biggest questions, the ones about what lies beyond everything, are the ones that make us truly think about what it means to exist at all. See you at the next frontier of human understanding.